Hi, I'm Leguma Bakari, Assistant Lecturer Statistics from Western Africa Statistical Training Center. Here today I'm going to introduce the concept of probability distribution, and we are going to split it into three parts. We are going to cover the first part, which is the concept of probability theory and distribution, and the second part is going to be the discrete probability distribution, and the third part, which will be the last, is going to be the continuous probability distribution. To begin with, we are going to touch a little bit about what is the probability theory, because in order to understand about the concept of probability distribution, first of all, we need to dig a bit about the probability. And we say probability is simply how likely something is to happen. Whenever we are unsure about the outcome of an event, we can talk about probabilities of certain outcomes, how likely they are. And in order to do that, there are three fundamental components or concepts which you need to know first. The first one is what is the random experiment or probability experiment, as well as what is a sample space and what is an event. So here, a random experiment, we say, is a mechanism that produces a definite outcome that cannot be predicted with certainty, while a sample space is associated with a random experiment, which is the set of all possible outcomes someone may encounter or may occur during the probability experiment. An event is a subset of a sample space, and this is an event of interest. And so far, we can say these are the three components which we need in probability computation. After the probability experiment, what we need second is what is a sample space and what is an event. And we should know the number of sample space as well as the number of an event in order to compute the probability. Because simply the probability of an event is a number of an event divided by a number of sample space, as it is displayed here in our screen. So to move forward, we can have a simple scenario here. Rolling an ordinary 6-sided die is a probability experiment. It is a famous example because we all know that a die have 6 faces, named 1 up to 6. So among all 6 from the probability of experiment, there is a chance one among them it can appear. But for which the actual outcome may be given a try of experiment cannot be predicted with a certainty. And this is, we are not sure if we are going to roll our die, the face which is going to appear will be 1, will be 2, will be 3, up to 6. Wherever it can happen, this is called an uncertainty situation, and it is a probability experiment. In such a situation, we wish to assign each outcome, such as rolling a 2, a face which is named 2, a number called the probability of an outcome that indicates how likely is that the outcome will occur. We need to understand that chance. How likely phase 2 will occur, or how likely phase 1 will occur, or 6 will occur, and all other events within the given sample space. Similar, we would like to assign the probability of any event, as I said before, from 1 up to 6. Rolling an even number, this now is an example because from a die we have 1, 2, up to 6. So we may choose my event is even number, which means 2, 4, and 6. How likely it may happen that you obtain an even number out of the experiment. We need to compute that one. So to construct a sample space out of that, we need to list down all possible outcomes from our probability of experiment. And we know that our experiments have 6 faces, so the possibility is to have a face 1, 2, 3, 4, 5, and 6. It is impossible to have an event out of those, and this is what we call a sample space, like how it is indicated here. And after obtaining sample space, we need now to count how many events it is possible. There is a possibility for them to happen in our given probability of experiment. What you obtain, we call it a number of sample space. Now, to find the event of interest, we need to define out of these elements of the sample space, which one do we have the interest with. Like this one, we may have an interest of an even number from the probability of experiment. And we know from 1 up to 6, the even number are 2, 4, and 6, which means now our number of event, which is the number of even number now, is equal to 3. In order to obtain the probability, now we need to take the ratio of number of event, which we call it A, divided by number of sample space. Now it is 3/6, and its simplest form is just a half. Maybe sometime also may be interested with an even number, but the condition is that even number must be greater than 3, must be greater than 2. Which means now if you combine the two premises, the only possibility for such numbers is 4 and 6. And the number of event now is 2. Now if you take 2 divided by total number of sample space, it is 2/6, and it will result into 1/3. This is a simple expression how you can compute a probability in simple scenarios. So in every discipline, there are some rules which may be applied in order to reach the computation of the conclusion. Again, in probability also, we have the so-called the axioms of probability. And these are 3. There is what we call positiveness, there is what we call certainty, and there is what we call additivity. For positiveness, it means the probability of any event is non-negative. It can be 0 or any other number greater than 0, but less than 1. That is the axiom number 1, which means it is impossible for us or for any of us to obtain a probability which is negative, but it is also impossible to obtain a probability which is greater than 1. That is the meaning of this limiting range. So probability must range between 0 and positive 1. When you get 0, under the statistical interpretation, it means such a thing, it is impossible to happen. There is no such possibility for it to happen. So we call it probability 0. And you may just say, like in our example of rolling a die, we know the die have a face 1 up to 6. But what if someone asked you to compute the probability of a face equals to number 7? Since it is not a part of the sample space, it is impossible for such an event to occur. So we say the probability of it is 0. And the second axiom, we call it certainty. Certainty is the probability of sample space. If your interest is all elements available in sample space, then we say the probability is 1. Which means now this builds the upper bound, the minimum obtained from the first axiom, or the maximum value obtained from the second axiom, which is 1. And if a scenario like this happen, under the statistical concept, we say this is a sure event. It must happen. It must happen because, like in our previous example of die, all events range from 1 up to 6. Now, if someone asked you what is the probability of obtaining number 1 or 2 or 3 or 4 or 5 or 6, since the answer must be one among those, we say that is a sure event because the probability of it is 1. The last axiom, we call it additivity. This may happen now if you have more than one event. A simplest form is to have 2 events. The condition of these 2 events, they must be mutually exclusive. There is no such a scenario that those 2 events, there is a chance they can happen together. If you have such kind of scenario, we say the probability of event 1 or 2, A or B, is equal to sum of the probability of those individual probabilities. So in a simple case, we say those are the 3 axioms of probability, which we say they are the truth about the probability. Whatever the foundation or the theory about the probability, they must cover these 3 axioms. They are always there. Now, having said a little bit about the probability theory, in order for us to understand the concept of probability distribution, we need to touch what we call the random variables. What is random variable? Random variable, it is a combination of 2 terminologies. There is a random and there is a variable. And we know variable is something which is the converse, the inverse or the opposite of constant, something which var allows us to take different values. But the term random is the one which can capture the concept of uncertainty. So when we are talking about a random variable, it means we are going to have a records or a data, but we cannot surely predict what will come next, since our problem must be in a random phenomenon. So a random variable, or other called stochastic variable, and this is the famous terminology used if your variable of interest involve time. It is called the stochastic variable. So random variable is a type of variable in statistics whose possible values depend on the outcomes of the certain random phenomena. This point here is very crucial, because if there is no random phenomena, then there is no random variable. And if there is no random variable, we'll see later on there is no probability experiment. Because the moment you don't have random, then you don't have probability. It is very crucial for this terminology to be inclusive. So we must make sure. That's why even those experiments which must result into probability, chances, or whatever, within it, you must avoid any kind of bias, and we must have a purely random for it to be a random variable. So since a random variable can take on different values, it is commonly labeled with a letter. We cannot label a random variable with something like 2 or 3, because those are fixed numbers. So we name it with a letter and an uppercase letter, which can signify that it take any values. It can be 1, it can be 2, it will depend with the domain or range of the random variable. So again here, since we have already talked about the concept of random variable can be split into two main types, the discrete as well as the continuous random variable. In nutshell here, we can say random variable are classified into discrete and continuous variable. The main difference between the two categories is the type possible values that each variable can take. We know the discrete take counted value, real numbers, while the continuous can take even fraction or decimals. We are going to classify it more during the session of scale of measurement. So the discrete random variable in nutshell is a variable whose values take only finite number of values. It is impossible for discrete random variable to have something like 1.2 or 1.5. You can have something like 0, 1, 5, 7, just a finite number. An example of a discrete random variable is a dice, because dice we can assign 1, we can assign 2, we can assign a 6, but no such a thing as a dice 4.5. That's why we say dice is a discrete random variable. Throwing a dice is a purely random experiment. The first condition, remember, in order for us to use the probability, we must have the random component. Since the dice can take only finite number of outcomes, 1, 2, 3, 4, up to 6, then dice outcome is a discrete random variable, as I pointed out earlier. So in nutshell, the discrete random variable is for counted values only. Remember this, because this is going to be the only discrepancy between discrete and the continuous. So this type of variable will result from a variable which is nominal scale in nature, and in some occasions the ordinal scale. That's why I said you're also going to touch a little bit about the scales of measurements. Again, what is a continuous random variable? Unlike a discrete random variable, continuous random variable can take an infinite number of possible values. If we say 1, the next counted number is 2. So you have only 2 values. But if we infinity from 1 up to 2, there are so many quantities you can have in between, 1.1, 1.11, and so on and so forth. So one of the examples of continuous variable is the variable length, or weight, or age. Length can be 12.2 centimeter, 1.2 meter. Weight can be 30.1 kilogram. As long as it can take decimal points, then we say that is a continuous variable. Something else which marks the difference, any continuous variable must have a unit of measurement. When you're talking about weight or height, for weight we can say a unit of measurement may be gram, it may be a kilogram, it may be a ton. For length, you can say a centimeter, a millimeter, and so on and so forth. For age, you can say a second, a year, month, weekly. As long as you can have a unit of measurement, that is the clear-cut definition or discrepancy which can tell you that this now we are dealing with is a continuous random variable, unlike the discrete. In discrete, the only thing you will have is count and not a measurement. So note the continuous variable is for measured values only, which must have a unit of measurement, as I said before. So the probability of certain outcome for continuous random variable is 0. This is the point which I'm going to clarify it later on, after what you're going to see for the density function as well as the mass function. So however, there is always a probability that a certain outcome will lie within an interval between two values. So worry not about this description here. Later on, we are going to clarify it more after seeing the so-called density function as well as the mass function. Having said that, now I can speak also a little bit about the scale of measurements of data. This point here now is very crucial, because once you understood this, you will understand the nature of all random variables and how you can figure them out in computation of your probability, and you have less confusion about a discrete and a continuous random variable.